All right, this is lesson 2.1. So we're starting Unit 2, just in case you're not already aware. Unit 2 is one of our shorter units. It only has 4 lessons, and then we spend a day reviewing, and then we will test. So the test for Unit 2 will be, depending on if you're A or B day, it'll be September 19th or 20th. Today we'll be focusing on the characteristics of functions. We'll be looking at graphs, and before we start though, I wanted to do a quick review of function notation. When you see some sort of function notation like f of x or g of x or c of x, remember that notation f of x is a y value. We use function notation for a few reasons, one of which is just because it preserves the input or the x value, but f of x itself is a y value. So when you see the function f of x equals x squared minus 3x plus 5, it's like y equals x squared minus 3x plus 5. So let's practice an evaluation. So when it says something like f of 3, that just means that you are going to substitute the value 3 into the function where you see the x. So in this case, it would be 3 squared minus 3 times 3 plus 5. And you could evaluate that either in your head or with a calculator. And if you do evaluate that, you should come up with the value 5. So f of 3 is 5. It doesn't have to be a number. You could also substitute in a variable. F of t just means put t into the function where you see the x. So it'd be t squared minus 3t plus 5. It could be other things as well. For example, f of x minus 2 looks really scary, but all that means is everywhere you see x, you're going to put x minus 2. So it would be x minus 2 squared minus 3 times x minus 2 plus 5. And you could simplify that if you needed to. So here is our same function, x squared minus 3x plus 5. Here's the graph of the function. It's a parabola, which you may have guessed because of the power 2 in the function. And f of 3 equals 5, we just calculated a moment ago. That has a corresponding part of the graph. F of 3 equals 5, it corresponds to the point on the graph 3, 5. In the x direction, 3 up 5. It's this point right here. And really all a graph is the collection of every single possible point that makes that function true, every possible y and x value that makes the function true. We can use this picture of the graph to find some other values of the function. F of 0, so that means when the x is 0, what's the y value that goes with that? Well, that would be the point right here. It would also be 5. F of 2, we would look for the x value 2, and the y value that goes with that for this function happens to be 3. Part C is a little bit different. In this one, we're looking for an x value, and we want to know what x value, or for which x value, is f of x equal to 3. So remember, f of x is a y value. We're wondering which x would cause the y to be 3. So up on our graph, a y value of 3 is right along here. It looks like we have 2 points on the graph, or 2 x values, that would make the y value be 3. And those 2 x values, it's x equals 1 and x equals 2. So either of those x values would work. So let's look at this function. This graph is displaying the amount charged by a photographer for a photo shoot. This function, we're calling it c of x. I'm just going to scoot this down a little bit. So the first part says, what is c of 3.5? So if we substitute 3.5 into this function, what what's the y value that goes with that? Well, 3.5 is like right between 3 and 4. So the y value that goes with that on our graph looks like it is 250. And what does that mean in this context of a photo shoot? Well, in this case, the x represents the time spent on the photo shoot, and the y value is the cost of the photo shoot. So in this context with this photographer, C of 3.5 equals 250 means that if a photo shoot is 3.5 hours, oh, I can spell, its cost would be $250. The second part is a little bit different. I'm telling you the value of the function. If the value of c of x is 400, what x is it going to be? So we're looking for the value of the function to be 400. That's a y value, 400. And it looks like we have a bit of a choice here. It could be 7 hours. It could be 6.5 hours. It could be really, if you look at it, any number between 6 and 7. So we could represent that as an inequality. The x has to be larger than 6 and smaller than 7. X is between 6 and 7. And you might have noticed that it can include 7. So we would have the equality part of that. So x is greater than 6 and x is less than or equal to 7. So in the context of our problem, what does that mean? Well, we could think of it like if you have $400 or have a budget of $400, you could have a photo shoot that is between 6 and 7 hours long. You'll all be seniors next year, and I'm sure you'll all have 6-hour-long photo shoots. Hooray! All right, so that was our little brief review. Now we're going to go into the characteristics of functions that we need to learn about today. These characteristics we'll actually use throughout the year as we study different function types. And the 4 that we're going to talk about today are end behavior, relative mins and maxes, intervals of increase and decrease, and the last one, intercepts. You probably are already familiar with that last one. The other 3 are probably new. So the first one is end behavior. The end behavior of a function is the behavior of the graph as x approaches positive or negative infinity. So essentially what we're saying is what is the y value of the graph doing as x goes to the far left or the far right. The notation looks like this. And it can be in different orders. For example, you could have the negative here and the positive here. You have to kind of pay attention to that, but it typically looks something like this. So what this is saying, or how I would read it, is to say as x approaches positive infinity, f of x approaches, and then we would fill in what it is approaching. So when you see this arrow, typically we use the word approaches. So the second one would say as x approaches negative infinity, f of x approaches, and then we would fill in wherever the function was going. So if I'm saying the word approaches, this is what the arrow is. It's approaching. Sometimes you'll also hear people say goes to. As x goes to negative infinity, f of x goes to. It's probably a little more proper to say approaches, but if you need to say goes to, that's fine. So here's our first function to look at. This is a cubic function, so it's a third power of x. So it's a little squiggly thing. So if we look at this first notation, it says as x approaches positive infinity. Well, that's saying as you go towards bigger and bigger x values, so as you go to the right, f of x approaches, and remember f of x is a y value, so f of x approaches, so we have to think about what the y value in this function is doing as we go farther and farther to the right. And in this case, the function is growing. It's going upwards very, very rapidly. The y value is approaching positive infinity. For that second statement, it is talking about as x goes towards or approaches negative infinity. Well, x would be going to the left if it was going towards negative infinity. And in this case, what this function is doing, you might notice, is that it is going down very, very rapidly. So the y value, or the f of x, would be approaching negative infinity. It's going downward. This is saying go right. This is saying go left. So on the right side, it's going up. On the left side, it's going down. And I think the concepts here aren't very hard. It's the notation that is sometimes a little bit tricky. So here is another function to practice. It looks a lot different than the last function in some ways, but in some ways it's similar. So the notation here you might notice is sort of flip-flopped from last time. It says f of x approaches, and our job is to fill in what it's approaching, as x approaches positive infinity. So this first statement is talking about the right side of the function. As x goes towards positive infinity, or in this direction, well, it looks like this function is getting closer and closer and closer to a value, a y value of 3. And sometimes it's hard to know exactly what the function is doing without having the equation of the function. But for this particular function, that is what's happening. It is getting closer and closer and closer to a y value of 3. So it's not going up or down, it's leveling out, if you will. On the other side, f of x approaches something as x goes towards negative infinity. This is talking about the left side of the function. On the left side of the function, as we go farther and farther to the left, this function is getting higher and higher. It is going up towards positive infinity. And remember, these are y values. Okay. We're going to look at two more functions here, and for these two, I'm not giving you the picture. We're going to actually use our graphing calculator to help us see what these two functions look like. So the first one, it's a quintic function. It's a fifth-powered function. So let's pull up my graphing calculator here. So if I want to graph this on my graphing calculator, because this function and many of the functions that we study this year are complicated functions that we don't necessarily graph by hand. We use technology to help us get a picture of what it looks like. So to graph it, you'll hit this y equals button. It's the far left upper button, y equals. Should bring up a screen like this. And you can just type in that function. The negative button is down here at the bottom. Negative. The X button is next to alpha, the green button. It's red on the screen right now. X, and then we can use our power button to the fifth power. And now you notice that it's still sort of up next to the 5. To get down out of the power, you have to go over. Half the time I forget to do that, and then I have to retype it. Plus 2, go back to your X button, and now we need the third power. And then go over, and finally minus 1. So we have our function in. And now to see the graph of that function, you just hit the graph button. My Zoom is kind of funny. If you're not getting a picture, it's probably because your window is set up zoomed into something in particular. So I'll hit the zoom button and you may need to hit the zoom button. And for this, we can go to number 6, zoom standard. And it will take us back to a little bit better window. So this thing kind of dips down and kind of curves back up a little bit, and then it goes down some more. So on your, back to your notation here, I have a little picture in the corner there. As x goes towards positive infinity, so we're thinking about as it goes towards positive infinity, that would be the right side of the function. This one is definitely going downward. And on the other side of the function, as x goes towards or approaches negative infinity, this function is shooting upwards very, very rapidly, so positive infinity. Okay, let's graph this other one in the graphing calculator. So I'll go back to my y equals screen, and you can hit clear to just get rid of that other function. We need to do 1/4 x to the 8th power minus x to the 6th power. On these calculators, you can get fractions if you use alpha f1, and that first choice is a fraction. But if you don't want to remember that or don't care if it looks like a fraction, you can just use division. 1 divided by 4 would be 1/4. And then x, and it kind of looks like maybe you're thinking that x is in the denominator. The calculator, though, treats that as a times x. So it would be okay to have the x right next to it. Okay, 1/4 x to the power 8. And then go over to get out of the power minus x to the 6th power. So now that we have it in, we can hit graph. And this function is kind of like a W. It's maybe hard to see on this your graphing calculator screen what it's doing, but it is dipping down. It's going up and over and then down again and then back up. Something like this. So almost like a W. So let's fill in our end behavior here. As x goes towards positive infinity, so as we go farther and farther to the right, this function is most definitely going upward towards positive infinity. And on the other side, as x goes towards negative infinity, that's talking about what's happening on the left side. This function is also going up. It is going upwards on both sides. So both of the sides of the function approach positive infinity. Okay, here's the one with a little bit of context. So this graph is showing us the temperature of a cup of coffee in degrees Celsius, and the x-axis is showing us how much time has passed. So at time 0, at the beginning, it's 90 degrees Celsius. Time 1, it has cooled down a bit to a little bit around 40 degrees Celsius, and then it continues to cool. So for our end behavior here, it says as x goes towards positive infinity, we want to know what our function is doing. And as we go farther and farther to the right, it looks like it's leveling out. And maybe we would say it's approaching somewhere around 20 degrees Celsius. So what does that mean in the context of this problem? Well, that would mean that the coffee is cooling down towards room temperature. Room temperature is just right around 20 degrees Celsius, like I think 21 degrees Celsius. So, all right, before we start our next characteristic of functions, I wanted to look at this little parabola. It's x squared minus 10x plus 23. This parabola has a minimum value of -2 right here. And that minimum value of -2 happens when x is equal to 5. So we might say that the point 5, -2 is the minimum of this parabola. Does this parabola have a maximum? Think about that for a second. And hopefully what you determined was that no, it does not have a maximum. Both of those ends are shooting up towards positive infinity. There is no largest value here. Well, here is another little function. This one is, it happens to be a cubic function, but this function, if you wanted to know if it had a maximum or a minimum, you might notice that it does not, because over here it's continuing downward, and over here on the right it's continuing upward. So it has no minimum or maximum. But what it does have is some relative extrema, relative minimum, and a relative maximum. And those 2 points are these 2 points, relative maximum right up here, and a relative minimum down here. So it's not the minimum value of the function per se, but in its neighborhood in the function, relative to the parts of the function close to it, it is a minimum or a maximum. So for the relative minimum, you might say that that relative minimum happens at the point 3, -8. Or another way, and maybe a preferred way of writing it, would be to say that f of 3 is equal to -8. It has a relative minimum value of -8, and that happens at the x value 3. The relative maximum is at the point 1, 0, or another way of writing it would be that f of 1 is equal to 0. So here's a function. Find the relative extrema. Well, if we're looking for a relative minimum, that would be right here. F of 2 is equal to -2, or you could write this. And this thing has 2 relative maxes. They actually also happen to just be maximums for this function, but they would also qualify as a relative max. We have f of 1 is equal to 0, and f of 3 is equal to 0. Or you could write the point like this. I would like to note that if the function had looked something like this instead, it would still have 2 relative maximums. This would be an absolute max here, but you could also call it a relative max, and then here would be another relative max. And then in this case, of course, it would also still have a relative min right there. Well, if we're using our calculator to help us graph these, it can be sometimes hard to determine exactly where the min or max is. And in fact, sometimes they're not at nice points. Sometimes they are irrational. They're, some decimal that you need to find. So I'm going to go to the graphing calculator again, and we're going to use this function x cubed minus 2x squared minus 5x plus 6 to see how to get our calculator to help us with this. So I'm going to go back to the y equals screen and put in this new function, which is x to the 3rd power, go down out of the power, minus 2x squared minus 5x plus 6. So our function is in. If we hit graph, it draws this lovely thing for us. So it looks a lot like our first example, but because we're using technology, it can be kind of hard to tell exactly where that max and min are happening. Maybe you're thinking the max is, oh, it's about at -1 and 1, 2, 3, 4, 5, 6, 7, 8, but maybe not exactly. And the min, the relative min is about at, let's see, 2, -1, 2, 3, 4. But let's get those exact values because it's not at those exact points. So if we're using our calculator, we're going to use this calc button right here, but we need the calc part of it, so we have to do second and then calc. Brings up the little calculate screen, and first we're going to find the maximum. So we're going to choose number 4. And when you do that, it asks you a few questions, 3 questions to be precise. So the first question it's asking you is a left bound. Well, your calculator just wants to know the general neighborhood of the maximum that you're looking for, because for one thing, a function could have more than one of these. So it needs you to help narrow down which area to look in. So you can scroll over. You see, if you can see that little cursor moving, and it's asking me for the left bound right here. So I'm going a little bit to the left of that maximum that I'm looking for, and then I hit enter. And now it's asking me for a right bound. So I want to go a little bit to the right of that maximum that I'm looking for. And then you can hit enter. And then the last thing it asks you is to guess. It just is asking you to go kind of close to that max and then hit enter again. And once you do that, it will pop up on the screen exactly what the maximum, or relative maximum in this case, is. So the maximum is happening at negative 0.786 for the x value, and the y value is at about 8.2. So I have that filled in right here. So the relative max, I'm just going to write it as a point, negative 0.786, and then 8.21. You could repeat that for the relative min, so back to the calculator. I'm going to do second calculate again. This time, choice number 3, the minimum. And again, it's going to ask me for a left bound and a right bound. So I go a little to the left of that minimum. It doesn't matter exactly where you're at, just to the left of it. And then a little bit to the right. Hit enter. And then a guess, just get kind of close to it, hit enter again. And the minimum is now up on your calculator screen. So 2.12 and 4.06, 2.12 for negative 4.06. So that would be the relative minimum value for the function. Oh. If you were having a hard time seeing that, you could always adjust the zoom or the window. You could zoom out. Sometimes that doesn't, if you zoom out, you kind of want to tell it where to center the zoom. We'll play more with zoom later, and it just zoomed way out. So we may not even be able to see our function very well. Yeah. Oh, it's still thinking. I broke my calculator. All right, well, we'll come back to that. Here's another function. When you graph it, it looks like this on your screen, and it can be hard to see what's happening here. Is it leveling out and going up? Is it have a little jog down and then go up? I mean, it's so small there that it's kind of hard to see exactly what's happening. So you could do a zoom box. So here it shows the little box. You can trace out a little box and have it just zoom into that box. And then when you do that, it makes it a little easier to see. This function goes up and it levels out for a second, like really briefly, instantaneously, really, and then it continues to go up. So it never turns around and goes back down like this. So it actually does not have any mins or maxes, relative or otherwise. So it is possible that if one of these functions that we're studying won't have a min or a max. And you just have to, you know, look at the function and make a decision about it. Let me see if my calculator's still broken. Yep. Good times. Okay. Here's a little bit of context for relative mins and maxes. This is showing the price of Bank of America stock. over time. So on this side, starting in March 2012, it kind of went up in price and then came down during the summer. It had a little peak in July, and then it sort of continued to grow into September and October and November, and then by January it was up pretty high. So if you're looking at this stock graph, you might be asking yourself, like, when would have been a good time to buy this stock? Well, it would have been a great time to buy in around June or around August of of 2012. Both of those were relative minimum values. And when you might want to sell is if you had sold here at one of these relative maxes, you could have potentially made money. So maybe in January would have been the best time to sell. So that's just a little bit of context for relative mins and maxes. All right, so we've covered the first two characteristics, end behavior and relative mins and maxes. Third one we're talking about today is intervals of increase or decrease. So when you're looking at a function, you can kind of read it like a sentence from left to right. Always think about it from left to right. So if I'm thinking about this function in particular, I might notice that it goes up or increases, and then it turns around and goes down or decreases, and then it turns around and goes up or increases. And those relative mins and maxes happen to be like where it changes directions. So for this function, if we were thinking about an interval of increase, well, the intervals of increase and decrease are always just portions of the domain. So we use x values to report those. For this one, its interval of increase would be from negative infinity, and it keeps increasing until it hits an x value of 2. So first interval of increase is from negative infinity to 2. And then it increases again beginning at the x value of 4. And it continues to increase from then on, so all the way up to infinity. And you could connect it with a u. This particular function has only one interval of decrease. It begins decreasing at the x value of 2, and it continues to decrease until it reaches an x value of 4. Again, really focus on using x values or the domain of the function as you're reporting intervals of increase or decrease. It would be on this particular function, it would be really common for me to see somebody make the error, well, it decreases from 3 to negative 1. Well, that's true. Its peak or its relative max is at 3, and then it goes down to a relative min of negative 1. But when we're talking about intervals of decrease and intervals of increase, we are talking about portions of the domain. So this would not be what you want to say. That would be incorrect. Focus on the x-axis or the domain. So here's one to try. This function is like a W. So it goes, and we're reading it left to right again. It decreases, and then it increases, and then it decreases, and then it increases. So if we're talking about the interval of increase, that would be, well, it begins increasing at the x value of 1, and it just increases between 1 and 2. And then it begins increasing again at 3 and continues to increase from then on. The interval of decrease, when the function is decreasing, well, at the beginning it's very much decreasing all the way up until it reaches an x value of 1, so from negative infinity to 1. And then it also decreases between 2 and 3. I oftentimes will write the intervals of increase and decrease like this on my x-axis as I'm thinking about it, because that helps me to focus on the x values and not accidentally grab a y value, because you should only be using x values for intervals of increase and decrease. Here is another little function. If we think about what is happening here from left to right, the function is increasing. It kind of flattens out, but it never decreases, and then it continues to increase. So this function is actually increasing everywhere from negative infinity to positive infinity, and it does not decrease. It has no interval of decrease. Last one of these, I think. F of x is equal to the negative absolute value of x minus 2 plus 3. I wanted to teach you how to use this in the graphing calculator, but since I broke my graphing calculator, I'll just do it by hand. You could do it in your calculator if you want. If you want to find the absolute value in your calculator, hit the math button, go over to the one that says NUM, which is just the second one over, and it's that first choice, ABS. So you could graph this in your graphing calculator. I'll graph it by hand, over 2, up 3, and it has a slope of 1. It's going downward. So it's this function. So if I'm thinking about the interval of increase and decrease, I would think about my function from left to right like a sentence. First it's going up, and then it turns around at that vertex and it's going down or decreasing. So it increases from negative infinity all the way to the x value of 2. So from negative infinity to 2, this is an increasing function. And then it turns around, and from 2 to infinity, it will decrease. So it has just one interval of increase and one interval of decrease. It goes up, and then it goes down. Okay, last one. And this one you already know, so it's not too hard. Last characteristic of a function is the intercepts. So a function can have x-intercepts and y-intercepts. X-intercepts are found on the x-axis. This function happens to have 4 of them. I would prefer very much for you to not just write -4, -2, 1, and 3. Write them as points. -4, 0. -2, 0. 1, 0, and 3, 0. Again, please don't just write -4, -2, 1, and 3. Write them as points. And then for the y-intercept, we would focus on the y-axis. It just has 1 in this case, and it's the point 0, -1. So I have a little question at the bottom. It says, could a function have more than one y-intercept? Would it be possible for a function to have more than one y-intercept? In this case, it only had 1. Is it always going to be that way? Or could it have 2 or 3, like we have in this case 4 x-intercepts? Think about that for a second, and hopefully you came to the conclusion that no, it cannot. In order to be a function, it would have to pass the vertical line test, so it will only have one one y-intercept. Okay, a couple to try. This first one, I'm looking for the x-intercept, so I'm focusing on the x-axis, and hopefully you notice that there is not an x-intercept. None. Please use the word none or no x-intercept or nada or it doesn't have one. Write something. Don't write 0. If you write 0, I'm going to think you mean that it has an x-intercept at the number 0. So please don't use the word 0 for this. You can use the word none or something similar to that. And for the y-intercept, we're looking for where it intersects with the y-axis. In this case, it would be the point 0, 2. And if we go down here, we're looking for the x and the y-intercept. Well, if we're focusing on the x-axis, you might notice it is at the point 0, 0. And in the y direction, it is also the point 0, 0. If it goes through the origin, it happens to be both an x and a y intercept because that's where the x and y axes intersect. Okay, so that's it. I mean, it's kind of a lot of stuff, but we will continue to use these characteristics and practice with them all year long. So the homework assignment is 2.1 characteristics of graphs and functions. I have posted an answer key if you would like to check yours or if you're stuck on one and you think that it might help you understand it. Otherwise, if you have questions, though, you can ask me in class at the beginning of class. So that is it for 2.1. Thank you.